Okay, off we go. Last time we were talking about, we just barely scratched the surface of getting started with Stokes' theorem, sort of the, what I'm going to call the second half of this enormous section. It's the first half in the book, whatever. We talked about this idea of what the convention is for how to orient boundaries, and keep in mind boundaries are always oriented things. When you're talking about vector line integrals and vector surface integrals, everything's got to be oriented, right? And so we've established various conventions. They're all arbitrary, but they all fit together in ways that are hard to talk about at this level. So they all have to be consistent, and they're also all heavily established. And so even though they are arbitrary, they are non-optional. So we talked about this basically right-hand rule of sorts. If you have an orientation on the surface, thumb in the direction of the normal vector of the surface, thumb in the direction of the orientation, that is, of the surface. And you look at how your fingers of your right hand, very important that it be the right hand, right? Left hand goes the other way, right? It's got to be the right hand. You look at how your fingers define a sort of a swirl, and then you look at how that swirl sideswipes up against that boundary curve. That's the correct orientation. Okay. All right. Picking up from there. I mean, it's all kind of repetition in some sense, down all the way down to our final big theorem, you might say. Because we've already seen all of these ideas in some form or another. We've already seen this idea that boundary circulation accumulates. Not on surfaces, right? But we've seen it for two-dimensional regions in the plane. And if you think about it, a two-dimensional region in the plane and a two-dimensional surface in space, not that different, right? They have boundaries that are curves. The orientations work in such a way that the induced orientation there and the induced orientation there point in opposite directions and therefore cancel. And again, laid out on the page very deliberately in sort of the exact same way to emphasize the strength of the analogy. Boundary circulation accumulates. Again, I guess I'll say. And again, whenever we have a quantity that accumulates, we know certain things. We know, now you can look at pictures and think through details if you'd like, but the punchline is going to be the same. Accumulating quantities behave like stuff. You can think of it as kind of, it's physically not, right? But you can think of it as being kind of a physical sort of a substance and distributed over the interior. And stuff has an associated density. Right? So this is what we call circulation density because it gives us the stuff of circulation, namely how much circulation around that boundary. So I got to emphasize boundary circulation per unit area of the little piece of surface whose boundary you're talking about, right? Stuff per unit size. That's what density is. Again, it requires a little bit of imagination. You got to be willing to, think flexibly about circulation being a stuff, which again, it doesn't look like it, and it isn't physically, but it behaves like it, and so it's very helpful to think of it that way. So that's my favorite by far, favorite way to think of what this is it is circulation density. And by the way, you can compute, and what it turns out to be is curl dot orientation unit normal. Now, how does that work? Well, it's a detailed computation. We could do it. I feel what's most important in a situation like this is to have intuition, geometric sense for what things look like. That's why I'm emphasizing those things. What does it look like? How should I think about it? That kind of thing. And the details of the computation are details. Right? Very important mathematically, not really so much in this course. Okay, so we have then our formula. For circulation density, we have the interpretation of how to think about it. And we're ready to kind of throw it all together. As, again, you probably expected, because that's the next step in this sort of template for theorem formation that we've done this 4 or 5 times, right, at this point in various different contexts. So, reminding, we have this quantity defined on surfaces. You give me a surface, I can say, let's look at the boundary, let's compute the circulation around that boundary of whatever vector field we're talking about. So boundary circulation. We observe that it is an accumulating quantity. That's that cancellation business. So the whole's the sum of the parts, and it behaves like stuff. And if it behaves like stuff, that stuff, each little piece of that stuff can be thought of as a density times size. Right? Stuff is stuff per unit size times size. So, boom, same strategy, right? Now, this is, again, with the focus on how to think about it. There's all sorts of little rigor problems here. If this were a strict formal math class, I wouldn't do it like this, right? But for intuition purposes, for what I think is going to serve you all best in the long run, I think this is a really nice way to think about it. And we have ourselves a theorem. And depending on how you like to write it, you can write Stokes' curl theorem like so. But after having written it that way, you do notice one kind of cool thing, and that is that this density, what we call the density, that's being multiplied by size, if you just kind of move the pairing around, like put some parentheses, it's multiplication. You can pair things up however you like. If you pair things up just a little differently, remember this is the ds vector. Nice little notational convenience. Also, arguably a very natural little notational shorthand. After all, both of these sort of elements of the ds vector are entirely determined by the domain. So they kind of belong together. Really. Depending how you like to think about things. So this is my sort of preferred way to write Stokes' curl theorem, is like this, a little bit more compact, a little bit more elegant, and there you go, big theorem. A lot in common with Green's theorem. And Green's theorem was about circulation and circulation density. This is about circulation and circulation density. Both computed, with one-dimensional integrals, okay, sitting inside of R2 versus R3. Yeah, that's a little different. Both computed alternatively with what you might call two-dimensional integrals. Okay, and then we can procedurally and structure, the way we compute them, the way we define them are a little bit different depending on if it lives in 3 dimensions, like here, versus if it lives in 2 dimensions. So, appropriately different details, but basically the same idea as Green's theorem. A lot of people think of this as a 3-dimensional Green's theorem. And that's a perfectly reasonable way to think about it. Again, it comes with asterisks. The vector field does have to be C1. Problems happen if it's not. And I'll show you one of those problems later. And it's gotta be so everywhere. Not so much as a single point of problem. If there is a single point of problem, okay, then all bets are off. Who knows? And weird things can happen. And again, we've already seen examples of that as well. And again, I'll show you another example in this context later. Okay, so let's do one. All right. Here's the question. I will point out, just like I did with the first example we did with Green's theorem, that, don't expect that the ideal, sort of the best, most efficient solution to the problem will be telegraphed in the statement of the problem, right? And certainly it's not in this case. In fact, if you were to kind of pull on the obvious thread here, you see the curve is given, already parameterized. It's very tempting to say, we know how to pull back a line integral through a parameterization. We have the parameterization. It's like it's almost suggesting that we should pull back through the parameterization. Compute it, chapter 6 style. And absolutely not. That's a pretty bad way to do it, and I think you can probably even see that coming. After all, this is x, which means that goes there and there. So there's going to be a cosine squared. So the integral's got potential to get weird. Right? So not an attractive option. So what we're going to do is we're going to think about this differently. First thing we're going to do is understand this parameterized curve. Here is our parameterized curve. You will notice, I'm sure, the cosine and sine. That's familiar, right? That was our very first parametric curve. Cosine comma sine. Unit circle in the xy plane. No problem. Oh, wait a minute. Here, there's a minus sign on the y coordinate. That represents a reflection through the through the xz plane, like that. And so what this is, hopefully no surprise, we talked about an example kind of like this some time ago, but this is just what you get when you take the good old regular unit circle in the xy plane and reflect it through the xz plane. And so what that is what I have drawn here, like so. Like that. Okay. All right. And now y'all will probably remember the very first thing we did when we were talking about Green's theorem. In that first example with Green's theorem, we came back up and we reminded ourselves, hey, wait a minute. This doesn't work for just any vector line integral. It's got to be a boundary. Non-negotiable. It says so right here. Boundary. Right? It really only works with a boundary. It's got to be a boundary. So we have to worry, is this a boundary? Now there's a subtlety here. Subtly, thinking back to when we did the analogous first example with Green's theorem, hey, the orientation was the wrong way. It's not a boundary. And we had to play games with orientations and minus signs. Kind of looks like it's oriented the wrong way here. Tempting to say this is not a boundary. Not so. 3 dimensions is different from 2 dimensions. We got a little bit more elbow room. We got 3 dimensions of space to move around in. And with that additional sort of elbow room, this in fact is a boundary. This is a boundary of this surface that I've got highlighted in green. And you might say, no, wait, that's not going the correct way. Isn't it supposed to go counterclockwise? No, it is not counterclockwise. A common misunderstanding of this, it's not counterclockwise. I guess you could say that it's going to generically, if you're going around the outside, it's going to look counterclockwise. But it's going to look counterclockwise if, as drawn, I'm looking at it from the same side that the surface orientation points. Right? But counterclockwise, what appears counterclockwise, if you look at it from underneath, it doesn't look counterclockwise anymore. So there isn't really a useful asterisk-less notion of clockwise and counterclockwise in 3 dimensions. Right? But if you play this right-hand rule game, if you look at this orientation downward, just choose the downward orientation for your new surface. Perfectly legal. It's our surface. We can make up any surface we want. Just looking to make a surface whose boundary is this purple curve. And if I choose to orient it downward, thumb in the direction of that chosen surface orientation, fingers of my right hand go in the correct direction. Everybody see the little hand gesture point there? It's subtle. A lot of people get hung up on this, and you got to make sure to think about these things in the right way and don't fall for the oversimplified, temptations. So this is, in fact, a boundary. No problem. Everybody's good? All right, sweet. So we got ourselves a boundary, and let's see here. What does the theorem says? The theorem says that if you're looking at a boundary circulation, then you can rewrite your integral as a flux of the curl of the original vector field. So let's just write that down. All right. Our curve is a boundary, and as such, that circulation is a flux of the curl. Yeah.
If it was 2D, that wouldn't be a boundary.
Yeah, well, I totally hear where you're coming from. I'm gonna change your phrasing a little bit. There is a totally different curve, right? So we can't say this is given in 3 dimensions. But yeah, if we had a curve that was clockwise, literally clockwise, in 2 dimensions, also unit circle, then yes, that is not a boundary. Correct. Is that satisfying? Mm-hmm. Okay. Anybody else? Yeah.
Sorry, could you explain what you just said one more time?
Oh yeah, she was asking about, we've got this curve here that we're tempted to call clockwise, at least if we're looking at it from above. And she's saying, well, what if we just had just the XY plane? What if this was not a 3-dimensional question? Then it's a totally different question, is the first part of my point. Totally different question. That curve in 2 dimensions, oriented clockwise, not a boundary. Because in 2 dimensions, we don't have, again, enough elbow room. We can't be like, oh, well, just think of it upside down. There is no upside down. There's only 2 dimensions. Does that make sense? Is everybody happy? Okay. All right. So, yeah, sweet. We've got ourselves a new integral to entertain. By the way, no magic here. No promise that this new integral will actually be better. Fingers crossed. Right? But if I take that vector field that we were given, if I compute the curl, works out really nicely. As it surprisingly often does. Not always. Surprisingly often. Okay. Don't forget, we did, in order to make the boundary story work out correctly, we already decided what our orientation was going to be. Our orientation was 0, 0, negative 1, downward. In other words, in order to make orientations work out. And so now that dot product, right, this gives us the other half of that dot product, which is easy to compute, which turns this into a super easy scalar surface integral. Right? We did the dot product. There's no vector aspect of this left. This is just a constant being integrated on a garden variety geometric shape that we already know the area of, and boom. So, very convenient solution to this problem. Again, if you look back at the statement of the question, if I were to pull back through the parameterization, I'm not saying it can't be done, and it might not even be undoable. It might even be sort of like, okay, a little tedious, but well, we can make it work. But, why go down that road when there is this much easier solution here? Yeah? Okay. All right. So, powerful computational tool. Now, I do want to talk again about this idea of an oriented density, and you may recall we talked about oriented density when we were doing the fundamental theorem of line integrals. It was a little bit of a weird take, I will confess, but really useful. I think really useful, like in an important, intuitive, in terms of making sense out of curl. If you want to have a geometric sense for what curl is, I think this idea of an oriented density is the path toward making sense out of that. At least it is for me. So, reminder, here's how we developed the fundamental theorem of line integrals. Change is an accumulating quantity which has an associated density. That density was gradient dot orientation, not the gradient. Gradient dot orientation. That's how the chapter 2 computation works. And then we make this same observation we just did for the Stokes' theorem. We observe that dot product with t times the scalar ds, that's exactly our dr vector. And so we rewrote like so. And now, instead of thinking of stuff as scalar density times scalar size, the little sort of additional little piece of flexibility and imagination that I asked of you then, and I ask again of you now, is let's move things around, just like we just did. And while instead of a scalar size, it makes sense to think of this as a oriented size. Likewise, let's think of this now as being an oriented density. Right? And I say oriented change density because change is the stuff that we're talking about. Right? Now, again, a kind of a weird take at the time. I just kind of made this observation and said, we'll come back and talk about that later. Here we are. I didn't really do anything with this at the time. So let me just point out, I'll come back, I'm going to skip over some things here, but I'm just going to point out, we're going to just do the exact same thing now for Stokes' theorem. Again, here's the way we first wrote Stokes' theorem. We noticed again that product that didn't really, that's not how the pieces fit together initially, but oh my gosh, look at that. That is literally exactly ds. And so again, we have this opportunity, instead of thinking of this as a scalar density times a scalar size, right? After we regroup, if we think of this as an oriented size, which again, that's what it is. Right? It's literally the product of the orientation and the size. It tells you the size by way of its magnitude, and it tells you the orientation by way of which direction it's pointing. So I think oriented size is a very natural way to think of that. And along those lines, let's think of this then as oriented density also. Just like with gradient and the fundamental theorem of line integrals. This time, of course, our stuff is circulation. And so I'm going to call this oriented circulation density. It's a mouthful, right? So, brain stretch. Weird way to think about it. Ultimately, I think very, very useful. Now, let me go back up. Hit what we skipped previously. What are the cool aspects of this oriented change density, aka the gradient vector? Well, again, it has a direction and it has a magnitude, and both of those have natural interpretations. And we walked through a bunch of details. This is, one of the sections, or kind of a half of a section out of chapter 2, was that, the magnitude is telling you, in some sense, how steep is this mountain that you're walking around on. It's sort of, in some sense, telling you, I'm going to say the magnitude of the change density, but it's not quite that. It's the magnitude in the ideal direction. Right? So again, if you're hiking around on the hill, if that's uphill like that, and if I walk that way, then yeah, sure, I experience the steepness, which is in fact the steepness of the mountain. But if I walk this way, right, the mountain can be as steep as it wants. I'm not experiencing that because I'm not going in the direction that the steepness is actually happening. Right? So when we say magnitude of the gradient, that's not your experience. Don't conflate that with this. Not what we're talking about. Right? But the magnitude is the change density in that ideal direction. And then the direction of the gradient is that maximal direction. Well, we get the same good fortune down here. If you want to make sense out of oriented circulation density, what does that look like geometrically? And again, now it's a vector, so it's got a magnitude and it's got a direction. And if I've already forgotten which colors I used. Okay, fine. The magnitude tells you how much sort of rotation density there is. In other words, at the point that you're looking at, there is some circulation happening there. And is it like a lot of circulation, like a little tornado? Or is it kind of just a gently turning, barely noticeable, right? Just a subtle sort of a rotation of the fluid. The magnitude tells you. And then the direction tells you in which direction, around what axis is that circulation, is that rotation happening. Okay, so totally analogous. All right, now let's draw a picture. What does this look like? Here you go. Here's our curl vector. Right, and that curl vector, again, tells you two things. It tells you, by way of its magnitude, it tells you how powerful of a rotation are we talking about. Is this a whole bunch of rotation or a subtle, gentle, barely there rotation? And by way of its direction, it tells you around what axis the rotation is happening. So, for example, here, like this is around a horizontal axis, right? This is also around a horizontal axis, but a different horizontal axis, right? This kind of a rotation. And then there's something like this is around a vertical axis. And then, of course, in general, it might be around any, who knows what, any arbitrary axis. The direction that the curl points tells you the direction that that axis points. Is that cool? Okay. Lot to digest, a lot to sort of chew on and try to get some geometric sense for, right? And so give yourself the time necessary to digest that idea and to see the analogy with gradient and, the whole uphill downhill thing. By the way, I'm going to draw a couple of pictures. I'm going to come back to these momentarily. Let me just go back to gradients for a moment. Let's talk about gradients. And let's suppose you have a gradient like so. Let me label. This is a gradient. Yep. All right. So that gradient is telling me how steep the mountain is. It's telling me which direction is uphill, but also how steep is the uphill. Okay. So does that mean that the magnitude there is how much steepness I'm going to experience? No, not at all. I might be going a totally different direction, right? I might be going that way. In which case, I don't experience any uphill. The mountain is still there. The mountain is still steep. I just don't experience it because I'm not going the right direction, right? On the other hand, same gradient, right? What if I were going that direction? Oh, well, now I'm definitely going to experience some of that steepness. Not the full amount of steepness. We do have a little bit of an angle, and there's a cosine of that angle, and so, you'll experience most, maybe, but not all of that steepness. Right? Okay, so with that in mind, same thing goes on with curl. Right? So here I have a rotating fluid. You can see, and this curl vector represents the oriented circulation density. It represents, the direction and the magnitude of that rotation of fluid. Y'all see the rotating fluid there. So, if I have a little piece of surface, will I pick up that amount of circulation per unit area? No, absolutely not. Right? I mean, maybe if you're oriented the right way, right? If your normal is in the same direction as the curl, then okay, yeah, sure. And by the way, notice what that means is the way the fluid is rotating and the way the boundary is kind of rotating line up, right? And all of this rotation of the fluid is literally along that curve. So yeah, you'll pick up a lot of circulation if they line up correctly. But and which, by the way, I think is as it should be, right? Makes sense, right? But what if your little piece of surface is oriented a different direction. Now, this is a hard thing to kind of visualize, but if the fluid is rotating like this, right? And if my boundary curve is going the same way, then yeah, sure, we pick up the circulation. But what if, and I hope I can do this, what if as the fluid rotates, what if I'm going around a boundary curve like this? And it's like, I mean, this isn't gonna, I mean, as I go around the curve, is the rotation is the rotation along the curve if the curve is doing this while the fluid is doing that? No, they're totally different directions, right? This sort of rotation of the fluid just doesn't line up with this, you might say, rotation of the boundary. And it's picked up very nicely with the dot product, right? So this dot product catches how the rotation is in the direction of the boundary. And this lack of dot product, right? Those are orthogonal, not parallel. That lack of lining up correctly detects how the rotation is simply not around that piece of fluid, that piece of boundary, So, totally analogous. I mean, now again, different, right? Of course, but very much analogous to how gradients have this orientation that you have to account for, right, when you're thinking about change and how stuff changes. So, now I hope that analogy will be helpful. By the way, I do think it's really important to have some geometric sense like this of, what does curl look like? Here's just for your consideration. Y'all remember we have a bunch of these boundary theorems, accumulation theorems, wholes the sum of the parts. We've done it a million times. I even made the observation the fundamental theorem of calculus is an accumulation theorem. Right? Okay. Would you feel like you have a good intuition and understanding of the fundamental theorem of calculus if you had no instinct, no geometric sense for what the derivative looks like? No, right? I mean, what kind of a Calc 1 class would that be if, they show you the fundamental theorem of calculus, and then you say, what's this thing called the derivative? And they say, well, there's various rules, you see, and you follow these little symbolic rules, and that's this thing called the derivative, and magic makes it work in the fundamental theorem of calculus. It doesn't make any sense, right? You have to have some geometric sense of what a derivative is for that to be an interesting statement, connection between two, ultimately connected but seemingly distant ideas to really have a good sense for what that theorem's saying. Right? You can't claim to understand Calc 1 if you don't know what the derivative looks like. And I say likewise, you can't really claim to have a good understanding of multivariable calculus, a good understanding of Stokes' theorem, if you don't have some geometric sense, like what I'm pointing at here, of what curl looks like, right? And I think this little exercise, that picture and these examples compared to these examples, right, are a nice way to get that sense of what curl looks like, and therefore why, let me just point here, why this theorem, that, circulation, I missed. Try that again. Circulation is a flux of curl. Why that makes sense. Why that kind of ought to be true. Okay. All right. Okay, so a lot to chew on, a lot to digest. Give yourself the opportunity. Take some time. Think it all through. Okay. All right, so real quick, some physical examples. We've already talked about in 2 dimensions. Right, we have Green's theorem and curl. It is basically kind of a way of getting your hands on the idea of how this leaf floating downstream, how is that leaf going to be sort of turning as it floats? Right, and again, this is a nice little exercise. I don't know, are there any little creeks on campus or anything around here? I'm not sure if there are. I know there's a lake over there somewhere. But anyway, if you ever get an opportunity, and if you see some little creek, pick a leaf off of a tree, or better, pick up a dead one already on the ground, right? Just drop it in the water, and it'll just float downstream. But as it floats downstream, it will rotate. It'll turn one direction or the other. And that's just telling you how the fluid has a rotational aspect in it, such as I've drawn here, and curl is what computes that. Okay. Likewise, in 3 dimensions, morally equivalent scenario. Now we've got to think up a different metaphor because leaves don't really float in 3 dimensions, right? So my favorite analogy is a balloon, and you go to a birthday party or whatever, and they have helium balloons and they're up on the ceiling, right? And then a few days later, that helium is leaked out just a little bit. It starts to come down. And then a few days after that, they're on the ground. But there's a sweet spot in the middle there where they're perfectly balanced and they just float. They're perfectly buoyant. Right? So imagine one of those. And the curl is going to tell you how those will rotate because of whatever the air currents, the flow of the fluid of air might happen to be. And it'll tell you, again, 2 things. That curl will tell you around what axis will it rotate and how much, how fast. I mean, obviously there's other constants involved, and we'd need to know the moment of inertia of the balloon, and we'd need to know some sort of probably a friction coefficient between the air and the rubber of the balloon. A lot of little details, but basically longer curl vector means more rotation. Shorter curl vector means less rotation. So totally analogous, just 3-dimensional instead of 2, oriented instead of a scalar. But same basic idea. Is that cool? Okay. There is a ton to say about magnetic fields, and this is not a physics class, and so I'm going to have to restrain myself to not say too much about this stuff. But there are some things that I think either y'all already know or will very soon have to know about the nature, the relationship between current and magnetic fields. And this is just the way the world works. It's super weird. Don't ask why. This is the way the world was put together, right? The philosophy class, not physics class, if you want to know why, right? But what we observe that happens is that if you have a flow of charged particles, what we call a current field, so a bunch of charged particles moving along, that creates a magnetic field. It just does. Again, nobody knows why. It just kind of is. And the magnetic field, in some sense, kind of goes sort of around. It kind of rotates around the current. Yeah, again, in some sense. Okay, so that's observed. Now, that said, let's write some things down. And this first topic, by the way, you'll notice, I'm sure you'll notice here, I've got this little sort of square of equations, just like we had a little square of equations when we were talking about gravity and then subsequently electric fields. Right? Well, electric fields and magnetic fields, well, they're closely connected. They have a lot in common. And they're very different, but they are analogous in how this little square of equations kind of works out. So the top equation, hopefully, is not a tough pitch. Ignore this constant on both sides. It's on both sides, perfectly legal. So pay no attention to that for the moment. All this first equation says basically is that current is the flux of the flow. Well, yeah, that's kind of the definition of flux. Right? If you have a vector field representing a flow of a fluid, the definition of flux is quantity of fluid per unit time passing through the surface. That was the whole point. I'll say that was the motivating example, right? And current literally says how much of this charged fluid, how much of this fluid of, let's say, electrons, right, but in general charged particles, how much per unit time is passing through a given surface. That's exactly what current is. Okay, so the top equation, again, is kind of a freebie. Empirically, we notice this right here, that if you have a surface with a boundary curve, the current of charged particles through that surface relates, and again, you can just measure this, to the circulation of the magnetic field around that boundary. Just go into the lab, and this is just works every time. It's steady state. It's got to be steady state. So again, just kind of an empirical observation. Now, when we were on this side of the square talking about gravity, we had this cool metaphor of gravitons, and it was very helpful to, in fact, make that left side of the equation actually kind of satisfying and believable. I have no such little crutch for us to use here. So this is just, I'm just going to have to again claim, well, it's empirical. That's just the way it is. Anyway, once we get down to circulation, well, circulation is a flux of circulation density. Stokes' theorem. That's straight up Stokes' theorem. Then we notice, having gone all the way around, that if these two integrals are the same, then their integrands have to be the same, because those two integrals are the same for whatever surface you might happen to pick, and the only way for that to work is, again, if the integrands are the same. And so this gives us two different takes on ultimately kind of the same statement. Right? They look pretty different. One's about circulation, one's about curl. They're totally different things. They're related, closely related, right? But they are totally different things. They're computed by totally different formulas. Circulation's computed with an integral. Curl's computed with a bunch of partial derivatives. Cosmetically, these don't look the same at all. Right? But we're able to connect them to each other. We're able to see how closely related these two equations are by literally Stokes' curl theorem right there. So for your consideration, if you have already taken an E&M class, or even better, if you have not yet but soon will be taking a E&M class, Stokes' theorem is extremely handy, extremely natural tool to help you understand magnetic fields. Just like Gauss's theorem is just off the charts useful, essential really, to have a full, good understanding of electric fields. Okay. All right. Okay. How we doing? Yeah.
What would be the surface in this example?
So pick whatever surface you like. So maybe I have a surface over here like this, right? And then it has a boundary. Oh, and I better orient it, hadn't I? Let's say it's oriented that way. That doesn't look very clear. Let me, just to be clear, kind of, that way into the page, right, if you will. And then it's got a boundary curve, and I always have to think it through. Okay, so the boundary is going to be oriented this way, like that. And so when I say, doesn't quite fit, there we go. When I say flux of the curl, the flux of the curl is through the surface, right? The curl, of course, you'll notice, the curl being the current field is literally this. So this is what I'm looking at the flux of, right? And what we're saying is that flux of that green vector field through that blue surface will be the same as the circulation of the magnetic field. And keep in mind, here's our magnetic field. That circulation of that magnetic field around the boundary. Yeah. Is that satisfying? Yeah. Everybody see what I'm talking about there? That's a lot to digest as well. And, again, when you get into your E&M class or your next E&M class, whatever the case may be, very, very useful. Okay, so we do have to talk about singularities. I'm going to be pretty quick with this. Just a reminder, we have this very serious constraint when we write down Stokes' theorem. The condition, very important, the vector field has to be C1, and I mean no exceptions, right? If there's any sort of a singularity, any failure of C1, continuous differentiability, all bets are off. It's a very delicate theorem in that sense. Very delicate. So here's the example. Whoops, too far. There we go. So thinking about a current and a wire, right? And we've talked previously about how if you have a current, right, that creates a magnetic field. Got to think through the orientations. It creates a magnetic field that kind of rotates around. Okay, so we discussed this originally in the context of just an unconstrained, unconfined fluid of charged particles, just like it's flowing around in the room or something, right? But of course, most flows of charged particles are actually pretty confined, right? We get current in wires most of the time. Not always, but most of the time. So here I'm thinking about the current being in a wire that's pointing in the direction of the z-axis. Just cause. Okay, alright, fine. So let's consider the limiting case though. Right? In the limiting case means that this wire, that, maybe it's 20 gauge, 28 gauge, whatever, depending on how thick or how thin, but it's going to have a certain amount of thickness, however little. There's a little bit of thickness there. Now imagine that wire gets thinner and thinner and thinner, and in the limit, what happens? The limiting case is that the magnetic field will look something like this, which, again, is kind of rotating around like that. Defined everywhere except not on the z-axis. The z-axis having no thickness, right? Zero thickness. So this is non-physical. It's not the way stuff works. Wires actually have a little bit of thickness. But anyway, here we have no thickness. All right, so here's the weird thing. This vector field, if you compute its curl, the curl is 0. Everywhere it's defined. Easy computation. It's just some partial derivatives. Punch it up. It's 0. Okay, so when we do a flux of this curl, if the curl is 0 everywhere over the entire surface, and we say, well, we're going to compute that flux, it's a flux of 0, right? It seems. Okay, full confession. All right. In fact, we do have, at the origin is on the z-axis. Okay, so there's this one little point. One little innocent, tiny little point, right? Where, technically it's not defined there. But you see, even with that one point, just one point being undefined, how's that going to affect this computation of this surface integral? Well, one point shouldn't make a difference. Feels like. And tempting to say that this flux integral would be 0. Whereas, on the other hand, if you were to take the actual magnetic field and compute the circulation, you would get 2 pi, not 0. And so you can see that one little point messed it all up. Just like, by the way, again, I do this thing in the notes where I deliberately write the layout of analogous examples to try to mimic the previous analogous examples. And so this has got a lot in common with an analogous, what goes wrong with the idea of a point mass, right? Creating a gravitational field, and how does that mess things up? Right? So very similar, very analogous. By the way, keep in mind that when we talk about curl, when we talk about curl, the idea of curl is that it is circulation density, oriented circulation density. It's telling us, this circulation that we compute around the boundary, it's telling us in some sense how much of that is where and going in what direction. Okay. And so if it's 0, again, that's why this looks like a problem. Okay. But we can fix this problem. We can fix this problem by imagining, just like, going back to the gravity situation with the point mass, mass represents flux, and it's like we have a single lump of flux at the origin where the point mass is. It's like that point mass creates a point lump of flux. And likewise here, the one-dimensional, fictional current through a curve, current not through a wire with thickness, but a current through a wire, through a one-dimensional curve. It's like, again, there's a focused stream of circulation. And so if you kind of add that in, and how you do that, and how do you make sense out of an integral of a kind of a discrete lump, there's some math that has to get written down, and you have to talk about delta functions, and it's totally fine. It's totally doable. It can be done. I think it takes some time. I don't think it's a good investment of time for us. But in the same way that we fixed this seeming contradiction of the divergence theorem with the idea of a lump of flux, likewise here we have a focused stream of circulation. And that's where the missing circulation is. It's in that one-dimensional focused curve, right, line of imaginary focused current. All right, enough of that. Okay, filling in a gap, something we did a long time ago. Now everything on the screen here is old news. We totally did a while ago. Just a quick reminder, we had this question of, we know that gradients are path independent, and we've established that path independent means that all closed circulations must be 0. So this was a relatively easy little trio of equivalences. And how do we test for that? And what we argued is that the local test is this right here. You can just compute the curl. This is in 2 dimensions, by the way. Just compute the curl. Something you can compute at any point without having to worry about other points. We call it a local test. And if it's 0 everywhere, boom, yes, that is a path-independent vector field, aka all the other green conditions. So nice little tool. And how did we do it? Well, we did it by observing that Green's theorem is exactly what I need to make that connection right there. Right, and other details of the argument, y'all can rewind the recordings and watch that again if you'd like. But that was the key point right there. Green's theorem allowed us to take that step right there. And then I kind of waved my hands at a local test in 3 dimensions. And let me just go ahead and go all the way down. Again, we have these 3 sort of clearly equivalent, regularity assumed, of course, but relatively easy to see equivalent conditions. And again, I claim that we have a local test, and the local test now is 3-dimensional curl. And why does this work? And I had to kind of throw up my hands and say, well, we don't really have the tool just yet. We will develop the appropriate tool later. And I just had to say, well, trust me. Right, and we did an example, and we invoked this local test and drew a conclusion in at least one example. We now have the tool that we need. It's no big deal. Stokes' theorem. Stokes' theorem, you will notice, literally and exactly tells us that boundary circulations, closed, therefore circulations, are flux of curl. And then you make the sort of analogous argument here. I mean, if the curl is such that all fluxes of it are all zero, no matter what surface you're looking at, how could that be? What could curl possibly be for all of its fluxes to be zero through every surface you could possibly imagine? Well, it's got to be zero. So same morally equivalent anyway argument there. And again, Stokes' theorem was that missing piece, and now that we have it, you see that this argument is not that different, if I can get this to cooperate, not that different from what we saw previously. By the way, this kind of reinforces the idea that I said before, that Stokes' theorem is really just kind of a three-dimensional version of Green's theorem that we saw in R2. Just highly analogous. Serving the same role. Is that cool? That's just closing a loop. Satisfying a previous foreshadowing. Everybody okay with that? Okay, new idea that we're going to segue into with an old idea. I'll tell you what I'm going to do. This takes a lot of space, so I am going to do this. Let's start with the old idea. Let's start with path independence. Everything in purple there is review, old idea. Go back to chapter 6. By the way, always a good idea to kind of be constantly referring back to things that we've done previously, to fill in blanks, make sure that as time goes on you don't want to forget the older stuff, and certainly in situations where it has a role to play in the current stuff, you want to make sure that you're really solid with that older stuff. So maybe want to go back and make sure that you're comfortable with all this stuff. But let's hit the highlights. The highlights are, if you agree on a fixed starting point and a fixed ending point, namely if you insist that we consider only curves that start and end at these given, agreed upon, same points. Well, if your one curve, you look at the line integral along that one curve, and your other curve, look at the line integral along that other curve, note both starting and ending as required at the same point. And we mentioned this idea called path independence, and what it means for a vector field to be path independent is that these two line integrals would have to be equal, no matter what green and blue curves you pick. Same starting and ending points, of course, you gotta follow the rules, right? But no matter, there's a bazillion different green and blue curves that start and end at the given points. Bazillions. And they will all give you the same value of the line integral for these special vector fields, right? These path-independent vector fields. What a property, right? That's wild. And again, first time I heard this, I was quite convinced that this was impossible. Come on, it's too much to ask. How could a vector field be that amazingly coincidental? And then, of course, we found that, yeah, there's actually a bunch of them, right? All gradients. Totally works. Okay. Said differently, if green and blue are equal, then green minus blue, which is orange, would have to be 0. That's just a different alternative way to say path independence. Okay, so old ideas. By the way, I do want to hit a point on orientation here real quick before we go on. Let me zoom in on this picture, and let's talk about these two green and blue curves. And now I'm going to ask rhetorically, but think about how you might like to answer. Are these green and blue curves oriented the same way, or are they oriented the opposite of each other? Now, one temptation is to say they're oriented kind of the same way. They start at the same point. They end at the same point. They're both going kind of up and to the right. You know? You might say in terms of their boundaries, because they both start at the same point. They both end at the same point. In terms of their boundaries, they kind of have the same kind of, in some sense, orientation. But, on the other hand, the green one is what you might call counterclockwise, and the blue one is what you might call clockwise. Said differently, as part of the boundary of the region that they sort of, define, they're kind of opposite. Right? It's a little bit weird fact of geometry that there is a point of view that says these have the same orientation, and there's a point of view that says they have opposite orientation. And this is weird and unsatisfying, and again, another thing that I kind of struggled with for a long time until I made the realization, and that is, the question doesn't actually make any sense. You can compare two orientations on a single curve. If you have two different curves, you can't compare. I mean, you can make something up arbitrarily, like we just did here. Both of the senses in which I compared the blue and green orientations were made up and arbitrary. Right? But truly, can you compare those orientations? No, they're different curves. They go through different points. The tangent vectors are completely different. No comparison. Okay. All right, but anyway, notice again that there's kind of two temptations. They're kind of the same in terms of their boundaries, kind of the opposite in terms of how they relate to the boundary of what they bound. Okay. All right. Everything that just happened, there is an analogous idea one dimension up. And this is going to give us this thing called surface independence. It's really wild. Okay, let's see if I can, there we go. Okay, so instead of talking about curves with shared boundary points, we're going to talk about surfaces with a shared boundary curve. And by the way, orientations matter. So I've got to indicate the orientation on that shared boundary. And now we're going to start thinking about surfaces, different surfaces that have this same shared boundary. Okay, well, here's one such surface. Call it S1. Little exercise for y'all to think through. The way I have the orientation set up for this shared purple boundary, this indicated upward orientation on S1. Thumb, swirls, side swipes, think it through. Little geometric challenge there. Think it through. It will give you this purple orientation on this purple boundary. And then here's another one. And again, there are endless such. But here's another one that's, I'm going to say kind of down here like that and oriented, I'm going to say upward. Tempting to call that the same orientation because they're both upward. Tempting to call them opposite orientations because one's outward, one's inward. Neither is absolutely right. They're both made up arbitrary nonsense. Right? So just keep that in mind, right? So be aware of these temptations. These are not the same, they're not different. They're really not to be compared. But they play these sort of opposite roles in how they connect to other things. Okay, so these two surfaces, there are special vector fields that amazingly make the green flux and the blue flux always the same. And we call these vector fields the special vector fields that do this. Special vector fields that make the green flux always equal to the blue flux. Shared boundary curve, of course. That's, again, very important. They've got to have exactly the right shared boundary curve. But still, billions and skillions of such surfaces, they'll all give you the same flux for these special vector fields. By the way, notice as well, another way to say that, if you look at this orange surface, it goes all the way around, which you'll notice is a boundary of that three-dimensional solid. Green equals blue can also be said as green minus blue equals 0. Amazing. Weird that this is possible. Again, kind of blows the mind on first inspection. How could this possibly be true? Right? Those are totally different surfaces. We're looking at the green surface has totally different points from the blue surface. These two integrals are computed over surfaces that barely even share any points. How can I insist for any vector fields that these must be equal? Sounds like nonsense. Certainly seemed like nonsense again to me the first time I saw it. But there's a lot of vector fields that do this, amazingly. All right, now again, I deliberately lay it out on the page so that the analogy will be emphasized, and I hope that's clear from what you're looking at here. This idea of surface independence, and I still owe you an explanation of how could this be possible. Show me an example of anything that does this, right? But and I'll do that. But my gosh, it lays out on the page morally exactly the same way as path independence, doesn't it? And so surface independent makes loads of sense as a term to describe this. All right, now before I show you the examples, I want to go to our diagram. Y'all remember this diagram here, and again, it's on the web page in the class materials folder. And I've made the claim in the past that this is what results from if you take the very sophisticated idea of integrals of differential forms and you boil off all the formalities and the rigor and the ugly, right? And just look at what remains in terms of how, but for working purposes, just rubber meets the road, what should go where, what connects to what in these powerful natural ways. And this is it, right? Very underappreciated in my opinion, right? This isn't in our textbook, and it's not in really any textbook that I remember seeing, and I don't understand why. It's bonkers useful, right? And we've talked before about how, this pattern of, this is in some sense the pattern that the fundamental theorem of line integrals is saying, and I've made the observation that, yep, and you know what? Same for the divergence theorem. It's the exact same pattern. Totally different geometry, totally different details of computation, but the pattern is the same. And by the way, now that we've done Stokes' theorem, same pattern. It's exactly the same pattern. Right? So very, very convenient, just for strategic purposes. Right? Y'all are here taking a class. You want to be able to solve the problems. You want to be able to do well on the exam. You want to be able to compute the stuff. Right? Oh my gosh, well this is your friend. Right? Noticing the patterns and having a layout of exactly what goes where to keep everything straight in your mind is awesome. Right? So I urge you to focus heavily on this layout of the objects that we've studied. Super useful. So anyway, let's talk about path independence, and I've done this before, but path independence lays out as, you want to think of it this way, when you have two curves that have the same starting and ending points, you get the same value for the line integral. Well, we just defined something called surface independence. Surface independence says if you have two surfaces with the same boundary curve, then you will get the same flux. The pattern is perfect. Right? So, how's that for cool? I think that's pretty cool, right? Why is this not in the textbook? I don't get it. Okay. Let's see here. Going back real quick, let me remind you as well, path independence lines up with a vector field being a gradient. So we're talking about the special vector fields. Path independent means it's a gradient. And it also means that curl is 0. We talked previously about this sort of coincidence, that under appropriate regularity, as long as there's no sort of, annoying singularities or gaps or discontinuities or, as long as everything's nice and regular, green, orange, and blue are always simultaneous. Again, pretty wild. And I made the claim previously, but now it'll actually make sense. Oh, whoops. This coincidence of these three simultaneous properties totally works one dimension over. In fact, and we're going to see this in a minute, every curl is surface independent. And every vector field whose divergence is 0 is surface independent. The pattern continues to hold. By the way, furthermore, in the following sense, we'll see how far we get with this. How am I going to show, or correction, how have I shown that gradients are always path independent? You can flip back in the notes and rewind the recordings, what have you. How did we show that gradients were always path independent? Well, we used the fundamental theorem of line integrals. That's how we showed it. And you look back and see how we did, and fundamental theorem of line integrals was the tool. How did I show that when curl is 0, that the vector field is path independent? Well, we did that with Stokes' curl theorem about 10 minutes ago. Okay, so those were our two tools. Not only do the results line up in the pattern, but the tools that you use to show those results also line up. So I can take this little road map of how we sort of understood the, what you might call cool one-dimensional vector fields. We can slide the road map over, and as this suggests, and it's going to turn out this way. We're going to see this, a little bit, the first part of it maybe today, but the rest on Thursday. The way we're going to show that every curl is surface independent is, as this pattern would seem to strongly suggest, Stokes' curl theorem is going to be how we're going to do that. Right? And likewise, how are we going to show that whenever divergence is 0, it's surface independent? Well, Gauss's divergence theorem is going to be the tool that does that. Right? So this is not only, this pattern is not only telling you which properties connect to which other properties, it's even hinting at us how to see those connections. All of that works too. So let's see this in action. Going back over to here, first thing I want to show, this thing got in the way. Let's look at these dark green, right? How do I show that every curl is surface independent? It says here I'm supposed to use Stokes' curl theorem. Indeed. Stokes' theorem totally does this for it. Let me get rid of the mess. That's just clutter. If we have a curl, if that's a curl, and if I want to show that this vector field is surface independent, if I want to show that these two fluxes are equal to each other, well, I'm going to have to compute this green flux, and I'm going to have to compute this blue flux. How am I going to compute that green flux? Well, it's a flux of a curl. How do you compute the flux of a curl? Stokes' theorem literally tells us that the flux of a curl is a line integral on the boundary. How am I going to compute this one over here? How am I going to compute a flux of a curl? Well, again, flux of a curl, Stokes' theorem tells us, is a line integral on the boundary. And because they have the same boundary, these green and blue integrals are computed by the same line integral, and therefore they're equal, and therefore we have shown surface independence. Right? So as the diagram predicts, yes, Stokes' curl theorem is what shows curls are always surface independent. Okay, so I think that's pretty wild, and we're probably out of time now. So we'll go ahead and call it here. Y'all have a good rest of your Tuesday, and see you on Thursday. Have a good one.